And let's pop up to the screen here. One of the things that people had asked about, and I had sent this particular RFO file to you, is how you might do path diagrams if your preferred platform is Lavaan or R. So I've sent this to you. Some of you don't do R, so I've commented this a bit so that you know what each line does. The basic interface with R is a line-by-line program. It's kind of its own language. You can write your own functions and do all kinds of computer programming things if you'd like. Inside here, you specify that you have a model that you want to run. If you're doing regression, there are linear models. Regression program will do a regression just like we know and love. But if we're doing Lavaan, this is the output from, say, an Onyx program or something you wrote. And to fit that model, we then say SEM and what's the name of the model and what's the name of the data set. And that then gives you this printout. So why don't I just step through this interactively. To run your program, you hit this little run button. And I've read in the data set, the first line has the variable information in it. And this is the head statement, tells me what the first two lines of code look like. This is the output from a regression model. And to see that output, we then say the summary command. And here's the output from a regression. And if we're looking at an SEM, we specify the model. So we run that. And to run that, to fit that model, we then use the SEM module. Excuse me. Okay. And to see the summary information on that, we can again use the summary command, and it will then show you the estimation and the standardized estimates and so forth. And we've talked a little bit about that. This is the standardized all is probably what you want for most of our applications in this class. There is another plot exercise out there I have commented it out because as far as I can tell, using the Lavaan plot statement, all you're ever going to get is a statement of the variables and the paths. So let me uncomment that. You can look at it. And this is all you get. You get the name of the variable and the path and so forth. And you do have the control to be able to say, I want to see the standardized coefficients for the raw ones. SumPlot works a little bit nicer. So if we call that up, it's going to give us, let me zoom this out so we can see it a bit. It's going to give us the variables and the little triangle, and it gives you multiple triangles because I think they didn't want to go through the computer programming effort of trying to have one triangle pointing at everything. But it does give you the variances and the error variances and values. And these are the coefficients for the unstandardized solution. And if you want the standardized, the parameter names, you can say estimate, and that will then give you the particular estimates that you have, the variable parameter names in there. So if you have a need for that, it's there. I don't find this graph particularly publication worthy. It looks kind of ugly to me. The text is too small and the boxes are too big and the variances are overlapping with the intercepts. You can save this and export it to something else like Illustrator. You can save this as a PDF or a TIFF file, and that'll be a vectorized version of the graph, and you can then twiddle it the way you'd like, but it's there for you. The other thing that I had sent you was an example of a regression, and you can get the path diagrams out for that. So let's run this model. And in order to get to the diagrammer, make this a full screen so it's as big as possible. there's a tab up here in the upper left-hand corner called Diagram, and you can say View Diagram. At which point it will show you a path diagram. Like Lavon plot, the M+ diagrammer will not show you intercepts or means. So it's not, I mean, it'll show you a growth curve, but it's not going to show you the means associated with the latent variables or the manifest variable intercepts. You can touch these and move them around a bit. You can up here in the View tab come in and say, I want to see the standardized estimates, and it will show you those. You can come in and rotate the entire path by saying rotate clockwise. You can rotate it counterclockwise if you'd like. That has the advantage that it's going to take the variance estimate and have it not overlap on the path here. The numbers in parentheses here are the standard errors. You can, if you like, turn that off and say show only the estimates under the view option. You can say show no estimates and you'll just have the picture. It can also have you show the parameter labels. So there's the name of the parameters inside the model. So that's quick and easy. You can, inside of M+, draw a diagram and then have it write the M+ program that corresponds to that diagram. Generally speaking, as beginning students of SEM, it's probably more to your advantage to do this in ONIX, because inside of ONIX, you can then specify the intercepts and the means for a growth model. So that's just a little bit of chatting for the first 15 minutes. Are there any other things that people want to talk about before we head into the material for today? Well, let's come back then and talk about growth and change a little bit more.
I have a question.
Yeah.
So after we draw a path diagram, so you suggested to use ONIX. So can we just directly copy and paste for publication, or do we need to do something else after we draw the diagram?
Well, it depends. All right, so to answer the question that's foremost in everyone's mind, for this class, no. It depends on how professional you want your diagrams to look. So one of the problems, say, with saving an ONIX program, an ONIX graph, and putting it in your Word document is that's what's called a JPEG. That is, it is a pixel representation. And we can talk for a little bit about how you can make your path diagrams for publication a little more friendly, because inside of this model, for example, you might want to change the thickness of these lines to correspond with the strength of the association.
Mm-hmm.
You might want to take some of these lines, particularly if it gets to be a complicated model, and start curving them rather than having them be straight lines. And those are all things you can do inside of Adobe Illustrator quite easily.
Mm-hmm.
All of the figures that I've made in the book here were done in Illustrator. You can do things like this all fixed to one curve that goes up and follows all the intercepts. This, especially if you have a whole bunch of times of measurement, like one data set that I publish a lot on has 8 times of measurement. Well,
Mm-hmm.
I'm graying these out so that they're not as strongly indicated in the diagram, so that you can see more of these. And this tells you, oh, by the way, it's 1, 1, 1, 1, 1. So it eliminates some redundancy, and that's often a little bit nice. So that's kind of where I'm at. Regardless of your platform, if it's R or ONIX or anything else, it's kind of nice to be able to come in as a vector graph and start editing it and making it really, really pretty. And for dissertations, you might as well, that's the other thing about writing your dissertation is you're going to be spending a lot of time playing with it, and there will be some things that you can do during your downtime, and editing a figure and making it look pretty is something that's pretty mindless, and you can do that when you don't really have the energy to write. So, anything else?
Really quickly, can we go back to the Levon,
Sure.
the R code?
Yep. And you should have a copy of this. I sent it to you all, but yeah.
Oh, thank you. I have a question about, so when you fit the SEM, you're fitting the model. Oh, wait, no, I'm sorry, up above.
Yeah. Yeah.
Let me see.
And then down here is where it gets fit.
Oh, maybe I didn't see this correctly. Oh, when you're fitting the regression. So that's just an example with the regression, but is that necessary to fit the SEM model? It's just
no.
Example,
that's just me saying, if you run it this way, you're going to get an unstandardized and standardized regression laid out. And if you do it inside of SEM, you're going to get the same darn numbers.
Okay, thank you. My Friday morning brain was a little confused.
All right. Okay, gang. I mean, this should give you enough to steal if your interests run more toward R, and some of yours do, I know. Okay, well, let's go back and talk a little bit more about growth. So as we're looking at the FM shift model, our beliefs about growth are that when you have none of this material, none of this growth, that there is no variance, and that means and variances, as the means increase, the variances are also increasing, but there is no particular form to this growth that I'm forcing this to have. That these could be anything. So for example, underneath a freely estimated factor mean model, it's possible that things will decrease at a given measurement occasion and then increase again. The key point is that as scores decrease, variation would also similarly decrease. And the free curve model also assumes that means and variances are tied together. However, it's never the case that all of the curves that individuals have go down to exactly one measurement occasion, to having zero variance. Even at an initial starting point, there is some variation from one individual to another. Now, there's two models that I'm showing you here. One is an orthogonal model that is perhaps best represented by this curve, because it says down here at the time that there's absolutely nothing of growth happening yet, I have some variance associated with the intercept. And this second model says, rather than concentrating on this part, I'm going to concentrate on one measurement occasion here, for example, because you'll notice in this diagram, the first measurement occasion doesn't have a loading. So this 31.59 over here is an estimate of the variation in scores between individuals at the first measurement occasion. And when I do this, the value that a person has here becomes correlated with the trajectory that the person has later. So in this case, the covariance between the intercept and the factor variable at the first measurement occasion is 3.61. This corresponds to a correlation of 0.64, because I've got a variance here, 3.61 divided by the square root of 31.59 times the square root of 1 is going to give me 0.64. Now, there's nothing magical about which measurement occasion you talk about as the reference point. Very frequently in longitudinal research, and people who are giving out grant money to people for longitudinal research, there is this belief that the first measurement occasion is appropriately taken as the reference occasion for the model. But there's nothing that should guarantee that. And I would also argue that if there's a correlation, if you're doing that, it's going to make it a little bit harder for you to compare the results of one study to the results of another study. The first argument that I would like to tell you about is philosophical. Often, maybe even in a data set like this, we're looking at children in kindergarten. And the implicit argument in the background is, if we would invest money and resources in children at a very young age, this would put them on a different trajectory, a better trajectory than they would otherwise have. A phenomenon called, by Campbell and Stanley, the rich get richer effect. That if I can put you up here, you're going to have a much better outcome than if you were down here. That argument says, the reason that you end up over here is because of where you were here. That it is what philosophers would call maybe an efficient cause. But you could just as easily say, I'm interested in the means and the variances that happen at the last measurement occasion. That would be kind of a teleological explanation. And I may have uttered it before, but within the context of this diagram, we seem to make teleological explanations of people all the time. That if someone has an alcoholism problem, we might say, how did they get to be an alcoholic? We might be interested in the previous story that happened to a person based on how they ended up. And as a result, you could just as easily say, I'm going to estimate the factor loading for the first measurement occasion, but I'm going to set the factor loading for the last measurement occasion to be 0. And that's going to give me a different correlation between slope and intercept, because at this last time of measurement, I have an awful lot of variation. The second thing I'd like you to know is, if we're all researchers and we're all doing longitudinal research, it might be the case that some researchers start their study in kindergarten and other researchers start their studies in the first grade. Well, if both of those researchers take the first measurement occasion as the reference point, one researcher is going to be talking about the correlation between slope and intercept here, and the other one's going to be talking about the correlation between slope and intercept here. Well, as the variance in growth increases, the correlation between slope and intercept is going to be higher for the second researcher than for the first. So if you want to compare across studies where the starting times are different, you might be better off looking at the uncorrelated, the orthogonal growth model, because that's going to have you in a common metric. This variance is going to be the same across studies. Sometimes this takes a little bit of time to digest. And the other thing that's nice about this part is we're starting to get into the material that people usually talk about when they say there's growth going on. The things I'd like to highlight for you is that maybe the slope-intercept model is too complex. Maybe the factor mean shift model adequately describes your data. And the answer to that question relies a bit on, gee, does this phenomenon demonstrate this ability to have a random intercept component? If you're looking at something that's fairly hardwired to people, like physical height or physical weight, it could well be that there is no random intercept for that person, and what you're looking at follows a single curve. If you're looking at something that's more psychological, that might be an ability or might be an opinion, perhaps there are some people out there who just have uniformly higher scores across all measurement occasions, and there is a random intercept. The conceptual interpretation of this intercept is that it is a shift, but that the shift is different for different people. Whereas in the FM shift model, everybody has one shift, this number right here, that applies across all measurement occasions. Fitting this free curve model often generates some questions from your committee, from grant reviewers, and from reviewers of your article, because you're not necessarily making any assumptions about the functional form. As I mentioned, this curve can go up, it can go down. You can have periods of plateaus and then increases. To me, that's the strength of this free curve model. There may be in life, in developmental life, periods of moratorium where no growth happens. It may be the case that people decrease in their scores, even in something like verbal ability. We know from, I used to be at the University of Iowa, things like the ACT, the Iowa Test of Basic Skills, they show some seasonality. If you test children in the fall, their scores decrease a little bit because they've been away from school for a while. This leads now that you're graduate students, there is a little tip if you're trying to time when you take the GREs, and that it is better for you to take the GREs in the fall, because the scoring of the GRE incorporates a bonus for the time of year that you have. You get a few extra points just for taking that test in the fall. But if your data set is a very small data set, if the number of measurement occasions isn't large, we might think that we can specify this model and make an assumption of the shape of the curve. And if that model fits the data well, hey, we have a new theory. And this gets us into linear slope models. And this is what a linear slope model looks like. So what we're doing here is we're estimating our random intercept factor just as we did before. But downstairs on these factor loadings, I'm going to fix all of these loadings to numeric values. And in this case, these numeric values are the amount of elapsed time since the first measurement occasion. So in this case, the children were tested 0.88 of a year at time 2 after they were tested at time 1, and 2.73 years after time 1 is when the time 3 testing happened, and 4.72. So if you want to fit these models, you will have to come in and actually note the amount of elapsed time that goes on. The shape of the curve now looks like this, that when I fit these models at the 0 time measurement, this time 1, I've got a covariance of 3.83, and I have a variance over here of 0.63 and a variance over here of 3.37. That gives me a correlation of 0.94 between the slope and intercept. Just as for regular old growth curves, mean and variance are tied together. As means increase, variances increase. Just as before, I can also choose a reference point for this measure, for this model. And I could say I'm going to fit linear growth, but it's instead of prediction, it's going to be post-diction, if you will, by setting this floating to 0 and measuring the amount of time with negative values before which, the other measurement occasions happen. That would also give me an equally well-fitting model. The chi-square is exactly the same, and the picture is exactly the same. I don't get into it in this class, but straight lines are only one of many options. I can, for example, fit quadratic factors as well by squaring these numbers and adding another circle and estimating variances and covariances among those. Why is linear growth popular? So if you go to the M+ website, if you go to the Amos website, if you look in published manuals, very frequently you will see people fitting straight lines. Well, this occurs for a variety of reasons. As I mentioned before, to some extent, this has to do with a poverty in the data set. If I have very few measurement occasions, or if I have very few people, or both, maybe straight lines is all I can do to characterize change. That's somewhat analogous to the fact that repeated measures ANOVA is most appropriate when you have small sample sizes. The other reason, though, to assume, to entertain a linear model is if you're looking at a linear model and your measurement occasions are not equally spaced, you could just think about analyzing this in tall format. So remember, in tall format, I'm going to take my data set that was wide, that had for each and every person was one row, and I had time 1, time 2, time 3, time 4, whisk 1, 2, 3, 4 as my variables. I'm now going to make a variable where I have a single variable and a time variable. And this output statement makes a new row. I can then go into proc mixed and specify this as a hierarchical linear model. Here I have the correlation between the intercept and time. And here I have the variance, 31.84. Slightly different than the intercept, but that's the variance of my intercept, the covariance of my intercept and the values, and the factor variance. Now, the reason that these things are slightly different than you get out of SEM has to do with the minimization that HLM is doing. And down here, these are my estimates of fixed effects, the means, the 19.96, 19.94 is what I got out of SEM, and 5.86 is the estimate of the mean over here. So you're getting the same things out of HLM as you're getting out of wide format. But the thing is maybe tall format is the way you want to go when you're analyzing things, if for each person, these time variables are different. So if I do a study, and I talked during office hours on Wednesday about this, if I'm doing a study and I have 5 measurements on every person, but the measurements are not equally spaced, like maybe for the first person, the second testing happened a week later, but for another person, the second testing happened a month later. I can feed that model into HLM. I can't feed that model into a wide format because the times become very, very sparse. But I can feed this into HLM because it's just going to draw straight lines for every person. I want to draw your attention to a caution that happens when people are doing things in wide format. And that is, if you're looking at measurement occasions are not time. 9 times out of 10, when people do things like use YouTube videos and look at examples, they copy what they see in the examples. And what is often done in the examples is to go, I'm going to fix these loadings to be 0, 1, 2, and 3. And that's counting measurement occasion as time. As a matter of fact, if you ask Amos to draw a diagram for you for measurement occasions, it's going to default to do something like that for you. And that's not necessarily going to be appropriate to your particular research question if you didn't space time out equally. So often what happens in longitudinal studies is we deliberately don't space these times out. Say you're using a community sample or the Psych 1 sample, it's really easy to say I'm going to do an initial testing and then maybe 2 weeks later I'm going to do another testing. But it's hard to get these other testings to also happen at 2-week intervals. You might actually, if you get grant money, come back and say, I want to test people a year later and maybe 6 months after that. Well, you can't come in and say, I'm going to set these loadings to be 0, 1, 2, 3, 4, because the gap in time between 1 and 2 is only 2 weeks, and the gap between 2 and 3 is a year. So you're going to have to find some numbers that represent the actual time. Is that okay? And here's the HLM model with those loadings as given. Another thing that people will do is shown in this model, and there are okay things about this, and there are problematic things about this. So how does this diagram differ from the model we had above? Well, the model we had above is what I would call the right way of doing it, because if you are going to agree that time 1 is your reference occasion. What's happened down here is they have fixed the loadings for the time to be equal to people's chronological ages. And what you're doing when you do that is this model is going to fit overall identically to what you have up here. And that's fine. But what you are doing is you're changing the reference occasion for the intercept. The reference occasion for the intercept is now what happens when the loading is 0. Well, they were 6.07 years old at time 1. This is an estimate of the correlation between the intercept and the slope when they were born. Now, that's not going to, that says there's a correlation of 0.21 on the data. That's a lot lower than what we had up here at age 6. The overall fit of the model is fine. It's like this SEM fits with exactly the same chi-square and fit statistics as the other ones. But the correlations between the slope and the intercept are different by quite a bit. It could happen that, in real world data sets, I've seen people do this, and you start to see negative correlations between slope and intercept. Well, how does that happen? Well, all of these lines, as you've seen, are coming together to a point, and after that point, they're just going to keep on going. So if this line were to continue on, it's going to start to be on top of the distribution rather than being on the bottom of the distribution of scores. So you see a negative correlation if these lines all happen to converge on one point before birth. Yay for people who do this, or we don't really care. The overall fit of the model is going to be fine, but are these numbers actually interpretable is a good question. Finally, you might say, if you're looking at these lines, they all kind of converge to a point of minimum intercept variance. So if I were to extend these lines again, you'd see there's kind of a bow tie effect. That the lines converge to a minimum, and after that point, if you were able to observe them, they would expand again. This point of minimum variance has a name in the growth curve literature. It's called the aperture. And at the aperture, the correlation between the slope and the intercept is 0. So in that respect, it is an analog to the orthogonal free curve model, except that in orthogonal linear models, we're also making the assumption that growth over the course of time follows a straight line. And this is a discussion of the aperture and the references to it. You can play with this model. You can specify an orthogonal model in the following way. I'm going to identify the model by freely estimating the loading at time 1 and freely estimating the loading at time 4. And then I'm going to put some constraints and say, well, the loading in here has to be equal to the proportion of time from time 1 to time 2 relative to all of this time. That amounts to putting some constraints on the loading at any time as being equal to my loading at time 1 plus the difference between one measurement occasion, like say measurement occasion 2, and the last time of measurement, divided by the entire span of time, time 4 minus time 1, multiplied by the loading at time t, the last time of measurement, minus the loading at time 1. If your computer program allows you to put constraints in there like this, that you say that time 2 is going to turn out to be this, and this is my nonlinear constraint. I need to change that to a 3, by the way. That model fits just as well. So now we've got these loadings. You have to be able to tell your computer program, oh, and this loading is actually equal to some number times loading 1 plus some number times loading 4. And that will give you an orthogonal model. And at the aperture, the correlation between the slope and the intercept is 0. Well, what's the value of this? Again, if you want, it will give you a parameterization of linear growth model that would be useful in comparing groups. It might answer the question, say, do boys have more of a random intercept variation in performance than girls? But all of these models of linear growth fit with identical chi-squares. So your choice of what you want to use is really pretty much key to the discussion you want to have. So we're getting down to time. Many times, you're interested in analyzing more than one group. So this is the next topic I would like to get into. To preview this, you will find that there are many ways that people in structural equation modeling characterize multiple groups. That there is no single one way to say, I'm going to set up multiple groups. Amos has a very flexible way for you to do that, and we'll walk through that. The question involved in multiple groups is whether the structural equation model from one group is the same as the structural equation model for another one. So one easy question is to say, are my regression weights across the groups going to be the same, the unstandardized regression weights? But a second question is the phenomenon itself, as measured by a factor model, actually the same phenomenon? Maybe it's the case that patterns of covariation for minorities or disadvantaged groups is actually some different phenomenon, is composed of an entirely different set of factor loadings than some other phenomenon. Or maybe in some populations, even the number of factors might be different. That what sits as a, say, a single factor for men might actually be 2 factors when women are considering the questions in the survey. And finally, in looking at multi-group SEMs, we're also interested in saying, can I draw a structural equation model as a way of characterizing group differences? In other words, we've talked kind of somewhat tongue-in-cheek about the men-are-slime hypothesis, that relative to women, men engage in more antisocial behaviors. They tend to engage them with more variation and higher levels. And is there a way that I could perhaps draw a structural equation model where at the end of the day, maybe the loadings are the same across men and women, but the mean for men is a lot different and the variance for men is a lot different. So those are kind of the goals that we're getting into when we look at growth. That also extends to the question of growth curve models, because a growth curve model is just a regular old confirmatory factor model with means for the latent variables. It's easiest to start thinking about this with a picture, and it's easiest to think about this as a scatter plot for when we're thinking about invariance. So here's the pictures that I've come up with across the years. Maybe it's the case that the slope and the measurement error and the intercept across 2 groups are actually the same. So, but that there are differences between men and women. Well, if that's the case, here I've drawn a little ellipse to denote the scatter plot of scores of women and another scatter plot to denote the scores of men. And in this, the standard deviation of women is the same as maybe the standard deviation of men, and the intercept, the mean for the x variable, is different for men than women. Well, if that's the case, that would be kind of nice. That would be a parsimonious way of explaining differences. I could also think about the variance of men as being larger than the variance of women. All that's going to do is to extend this scatter plot out a bit more relative to the women, but the same law, the same relationship, the same regression line governs the 2 of them. Second scenario, maybe only the slope is invariant. So if I'm looking at two variables, men and women, and I have an x variable and a y variable, the intercept for men is higher. So even though the slopes of these 2 lines are the same, if men had none of whatever this x variable is, they would still score higher. They would still engage in more drinking behaviors, say, than women. But still, as scientists, we can say the same law governs these 2 groups in the sense that the unstandardized regression weight is going to be the same. It helps to go back and talk a little bit about picture A for a minute. If the variances of women and the variances of men are the same, both the unstandardized regression weight and the standardized regression weight will be the same. If, however, men are a lot more variable than women, the standardized coefficient for men is going to be higher than the standardized coefficient for women. And that's because there's more variation on the x variable in one population than another. Downstairs here, the same thing happens, that if the slopes are invariant, the slopes are the same, but the variances could be appreciably different. only the unstandardized regression rate is what we should be comparing in our analysis. And the third case is to consider the fact then that a fundamentally different regression applies to the two populations. So in this example, here's the scatter plot for women, and here's the scatter plot for men. Well, the slope, the unstandardized regression rate for women is different than the unstandardized regression rate for men. The amount of variance in men is different than the amount of variance in women. And the intercepts are different. So over the course of years, before we get into structural equation modeling, it kind of helps to start the discussion exactly here at just a regression, a single predictor, and a single criterion. Are there questions about this? I see we're at time, and we'll continue this to the case of two regression groups and talk a little bit about these models in terms of their equality constraints in a multi-group setting. And that's where we'll take it up. I have office hours now. Happy to talk with you.